Alright, this is the video for lesson 2.1, functions. We have 4 learning targets we need to hit. You can see them here. And please, at any time, pause the video. Make sure you write and write along with me. Pause if you have questions and write them down so you can ask them later. Don't simply just watch the video expecting to learn. Try to actively participate as you watch the video. So, Chapter 2 in general is about functions, but in particular, Section 2.1 is hopefully for most of you a reminder of much of what you've learned already regarding functions, and possibly introducing some new topics here, especially with piecewise functions and evaluating a difference quotient. So I would like to start by reviewing with you some of the ideas of a function. This definition right here comes straight out of the textbook. So a function is a rule, and when we say rule, try to think about that. One connection you can make is like a mathematical expression is a rule, like a number times 5 or a number minus 4 divided by 3. Those are all mathematical rules. It tells you to perform some kind of mathematical operation. So a rule that assigns to each element in a set A exactly one element called f of x in a set B. Now I know sometimes it's hard to just straight up read a definition, a mathematical definition nonetheless, and make a lot of sense out of it. But you may have heard the phrase also, a function is a rule that assigns for each input exactly one output. You can think about it like that. The key here that's really important is exactly one output. So for each input, this function or this rule assigns exactly one output for that input. A lot of students like to think about a function, visually at least, as a machine. So we have an input, some value for x that goes into the function here. And again, when you think about function, it's a rule. And by rule, it's some kind of mathematical operation that takes the input, works it over through that rule using some mathematical operations, and produces, in this case, exactly one output here called f of x. And a couple other words for these: set A input or domain, that's the set of all possible inputs. And then range is the set of all possible outputs. And hopefully this is not new, but more of a quick review of some things that you may have heard at one time regarding functions. Your homework is going to begin with having you practice evaluating a function. Again, much of what you hopefully have done before. So right now this is the rule that defines the function, and you're familiar, I would assume, with function notation, f of x. So the name of the function is f, and then this is a function of x. So you read it out loud, f of x, but really it's a function f, a function defined in x. So what we need to do is evaluate the function at these several values, f of 2, f of a, f of x minus 2. So if you remember, anything inside the parentheses, the input. So we are going to evaluate the function using an input of 2 for this first part. What I like to do, even with simple numbers and simple integers, is when you are about to evaluate a function, to rewrite the function using empty sets of parentheses anywhere there's an x. So instead of f of x, I'm going to say f of some input is equal to 3 multiplied by that input squared minus 2 multiplied by that input minus 4. And then you can put whatever input you want. You could put a 2 in there, you could put an a in there, you can put an x minus 2. Anytime you have an empty set of parentheses is where that input is going to go. So f of 2 would be 3 times 4 minus 4 minus 4. So this is 12 minus 8, which is 4. So we would say the function f evaluated with an input of 2 is equal to 4. F of 2 is equal to 4. Another way of representing this same relation is an input-output table. Instead of x and y, we could say x and f of x rather. When we plugged in a 2 for x, we got a 4 for f of x. So that represents a coordinate location if we wanted to graph it. 2, 4 is another way to think about this relation here. Now, if I wanted to do f of a, again, I would recommend, especially when we start to use a little more complicated expressions as inputs, that you rewrite the function using empty parentheses. So f of something is equal to 3 multiplied by that something squared minus 2 times that something minus 4. So we're going to evaluate the same function again, but remember we're trying to evaluate f of a. We're trying to figure out what f of a equals. So now I can use an input of a, and then use order of operations to evaluate. And since these are not like terms, none of the terms can be combined, so this would be f of a. Now f of a plus h. What is that? So again, when you evaluate a function, I would recommend you rewrite the function with empty sets of parentheses anywhere there was an x, because now our input is a plus h. And we evaluate still. And we simplify as much as we can. Here, what simplify means getting rid of the parentheses using the distributive property. So 3 times, and then a plus h squared is really a plus h multiplied by another a plus h minus 2a minus 2h. I just distributed the negative 2 there. And then minus 4. And a times h multiplied by a times h. If you use the distributive property, you're going to get a squared plus 2ah plus h squared. And finally, distribute the 3. And there are no like terms in this expression. So that's the value of the function f using an input of a plus h. So that's the first part of where we're going in this lesson, evaluating a function. I'm sure you've had lots of practice evaluating functions at integer values, like finding f of 2. You may not have had as much practice evaluating functions at expressions like a or a plus h, but that is a major component of this first unit, is evaluating a function. Okay. Along the same vein, this is our second learning target, evaluate a piecewise function. A piecewise function is a function that is defined in several different rules. So we have a rule of x minus 3 or a rule of x squared, and here we have a third one, a rule of 4x plus 1. So a piecewise function has several rules dependent on certain values of x right here. Now, one thing that's really important to keep in mind that piecewise functions are just that, they are functions. And if you remember the definition that we talked about a few minutes ago of a function, one input means one output. For every one input, there's exactly one output. One of the most common mistakes students make when evaluating piecewise functions is taking an input and trying to plug it into all three pieces at the same time. That defeats the definition, or goes against the definition of a function where we have one input giving us one output. If I took this -6 and plugged it into all three pieces of that function, it's going to give me three different outputs. Hence, it wouldn't be a function. So that's where these definitions are critical. It's saying if your input, and by input I mean this, in this case we're looking at the input of -6 right here. So if the input is less than -2, then you only plug that input into this rule. If the input is between -2 and 3, then you only plug it into this rule. If the input is greater than 3, you only plug it into that rule. So you are only going to plug an input into one of these three pieces at a time, not into all three, and it depends on what the value of the input is. So for this first one, f of -6, I have to look at where that fits in these definitions here. -6 is less than -2. -6 is less than -2, so it fits into that definition, which means I'm going to plug that -6 into that rule. So x minus 3 means, remember what we did with that last problem. Anytime there's a variable, you're going to make an empty set of parentheses. So instead of x minus 3, it's something minus 3, and that something is -6. And we get -9. Now for the second input, -2, we got to look carefully because I see a -2 here, but also a -2 here. So it depends on the inequality. For this top inequality, x has to be strictly less than -2, not equal to -2, whereas here, x is greater than or equal to -2. So the -2 fits into this inequality, which means it's going to be evaluated using that rule, x squared. So that rule says the input squared, in this case the input is -2, -2 squared is 4. Again, remember, one input gives you one output. Now the last one, f of 0. 0 is our input, so we need to figure out where that fits in one of these three inequalities, and it fits in the middle one. 0 is between -2 and 3. So if our input is between -2 and 3, then we use that rule to evaluate the function. So it's the same rule as we did in the just up above. It's the input squared, and in this case the input is 0. 0 squared is 0. So at this point in chapter 2 for section 2.1, we are only evaluating piecewise functions. In the next section, 2.2, we are going to learn how to graph a piecewise function, but for right now we're just evaluating. So the important thing to remember when evaluating a piecewise function is one input, one output, because they are functions. Okay. The third learning target is evaluating a difference quotient, what's called the difference quotient. I want to give you a little bit of a background before we just jump straight into the formula. So a difference quotient stems from looking at the rate of change of functions. Now you've spent, I'm sure, a great deal of time exploring linear functions. Linear functions have a constant rate of change. If I look at this point to that point, to that point, to that point, the rate of change at any point in this function is constant. It's known as the slope. And you all hopefully are familiar with, you may not remember it, but you're familiar with the slope formula for a constant rate of change. It's right here. But we explore functions in Math 1050 that are not linear, But we still like to think about the rate of change of those functions. So what about functions that do not have a constant rate of change? So something like this. This function doesn't have a constant rate of change. And let's get that back here. Okay. So if we look between these 2 points for the rate of change, and then between these 2 points and then these 2 points, the rate of change looks like is increasing. It's not the same rate of change between any 2 points, and there's really no linear part of this also. It's kind of curves up like that. So because it doesn't have a constant rate of change, what we can explore, and we'll talk a little bit more in detail about this in section 2.4, it's called the average rate of change, but we're kind of setting the groundwork here in section 2.1. If I took a value here and said, all right, this is an x value of a, so then the function value, assuming this is the function f, if I plug a into the function f, then here I would get f of a. Now if I went a certain horizontal distance from that point a, and I'm going to call it h, if I traveled a horizontal distance along the x-axis, then here I would have a plus whatever horizontal distance I just traveled. So then this x value is a plus h. So then the function value, if that's evaluated into the function, would be f of a plus h. So the difference quotient, what it does is it considers the slope of a line between those 2 points. It's what's known as a secant line. If a line goes through 2 points of a graph, we call that a secant line. And the difference quotient, in a nutshell, is evaluating the slope of that secant line. And so using the same formula that we used up here for the slope of a line, it's the difference in y values, which is f of a plus h minus f of a, divided by the difference in x values, which is a plus h minus a, which brings us to the difference quotient formula, f of a plus h minus f of a, and then here the a's are going to cancel in the denominator, so you have h. This is the formula you will see in your textbook in this section of your homework when it asks you to evaluate the difference quotient. And what essentially all it is finding the slope of a line between 2 points on a function that does not have a constant rate of change. And so to practice, here is an example. We have been given a function, 3x minus 4, and they're asking us to evaluate the difference quotient for that function. Now before we get into what this looks like algebraically, just something to consider. Not that this would be an acceptable way to answer this question on an exam. You'd still need to show all the work. However, this is a linear function. If we were to graph 3x minus 4 as a y-intercept of negative 4 and a slope of 3 over 1, and remember what the difference quotient is. The difference quotient is the slope of a secant line between 2 points. Well, any 2 points on this function is going to have the same slope, and that slope is 3. Anywhere on that function, the slope is 3, hence the difference quotient is also going to be 3, because between any 2 points on that line, we have a slope of 3. Now that being said, we still need to evaluate the difference quotient. This is what it looks like. What I would recommend, excuse me, is you kind of break this up into several parts. First of all, we need to know what f of a is, and then we need to know what f of a plus h is. So if f of x is 3x minus 4, then what is f of a, and what is f of a plus h? Well, f of a is 3 times an input. Remember, when we're evaluating a function, we take those x's or the variable, in this case it's x, we take the variable and turn it into an empty parenthesis, and then we just input whatever the input is into that empty parenthesis. So it's a, we get 3a minus 4. For f of a plus h, we rewrite the function instead of 3x minus 4, 3 parenthesis minus 4, and now the input is a plus h. So we get 3a plus 3h minus 4. Now that we have both of those pieces, I'm going to replace in the difference quotient, I'm going to replace on the top left, instead of f of a plus h, you can replace it now with this expression because they're equivalent. So 3a plus 3h minus 4. Then instead of subtracting f of a, we can subtract this expression because those are equivalent. So subtract, and this is another common mistake. When you're subtracting an entire expression like this, you need to make sure that you subtract the expression set aside in parentheses, so you can remember to distribute the minus sign. And then that's divided by h. And then when we simplify in the numerator, we distribute that minus sign into the parenthesis. And what happens here, and this is something to keep in mind, and always try to remember when you're evaluating a difference quotient, at this point, once you've simplified, any term that does not have an h should cancel with an opposite term. What I mean is this doesn't have an h, so it cancels 3a, negative 4, positive 4. The only terms that should be left in the numerator are terms that have a factor of h. So now we have 3h divided by h. We can cancel out that. And we get an answer of 3, which we anticipated. Again, going back to the start of this problem, the function 3x minus 4 has a constant rate of change of 3, so we would assume that the difference quotient is always going to be 3 for this function. But looking at a different type of function, 4x squared minus 3, 4x squared minus 3 is a quadratic function. Looks something like this. So depending on which 2 points you choose, the difference quotient is going to change depending on the value of h and where you are. So what I mean, for example, is these 2 points, the secant line would look like that, whereas if we choose these 2 points, the secant line would look like that. So this certainly does not have a constant rate of change. So to talk about the rate of change of the function in general, we use a difference quotient. Start the same way. We need to figure out what f of a equals, and we also need to figure out what f of a plus h is equal to. So the function is 4 multiplied by an input squared minus 3, and in this case the input is a. Now, well, let me finish before we move down here. So a squared is, or a to the second power is a squared. 4 times a squared is 4a squared minus 3. Now with a plus h, it's the same function. The function is 4 multiplied by an input squared minus 3. In this case, the input is a plus h. And then a plus h to the second power is a plus h multiplied by a plus h. And if you use the distributive property there, you're going to get a squared plus 2ah plus h squared. So we have 4a squared plus 8ah plus 4h squared minus 3. Okay, now that we have those 2 pieces done, we can substitute them into the difference quotient formula. Again, in the top left, rather than f of a plus h, we can substitute this expression now because they're equivalent. So the top left is going to be 4a squared plus 8ah plus 4h squared minus 3. Now we need to subtract f of a. So subtracting f of a means we're subtracting that expression. And again, when you are subtracting an algebraic expression, make sure you subtract the entire expression set aside in a parenthesis. And then simplifying here, this is going to turn into a negative 4a squared when you distribute the minus sign, so the 4a squared are going to cancel. This becomes a positive 3 when you distribute the minus sign, so that positive 3 is going to cancel with the negative 3. So you're left with 8h plus 4h squared divided by h. And one thing we can do now in the numerator is both of the terms that are left have a factor of h, and so that factor can be factored out. And then it can be canceled with the h in the denominator. So the final answer is 8a plus 4h. That's the difference quotient. And again, we'll see a little more detail of some practical uses of difference quotient in section 2.4 when we talk about what's called average rate of change. Really, they wanted to introduce difference quotient early on to set you up for section 2.4, but also to help practice evaluating a function, because that's essentially what we're doing here, is evaluating functions. Okay, the last learning target is finding the domain of the function. We talked at the beginning of this lesson that the domain is the set of all possible input values. So it's what's going into the function. And oftentimes that's a very important thing to consider, is what is your domain. And so I've got a couple of examples to look at here. The first one, f of x equals 4x minus 3. This is a linear function, and it has one spot for an input right here for x. And we need to think about this rule that's being described, 4x minus 3. And if we were to describe this rule verbally, what happens here is we have an input that's being multiplied by 4, and then you subtract 3. So we got to think, are there values of x where that's not going to work? Are there values of x that I can't multiply by 4 and then subtract 3? And the answer is no. You can multiply any number by 4 and then subtract 3. There are no values of x that would not work as a possible input. So in this case, the domain is any real number. You can use any real number you want as an input for x to multiply by 4. So a couple ways you can represent this. Domain, you could simply state all real numbers. There's a type of notation called set notation, where the domain is all values of x such that x belongs to the set of all real numbers. You could use set notation like this. The preferred method, at least in this textbook, the preferred notation and the notation you'll be expected to use on an exam or a final exam is called interval notation. And hopefully you're a bit familiar with interval notation from previous math courses. But interval notation really stems from the real number line. So if we think real number line, we have 0, 1, -1, and so forth. If the domain is all real numbers, then the whole number line is colored in or bolded in if you want it, or highlighted. And so an interval is exactly what it sounds like. It's a lowest number and a highest number described by what this number line is. So the lowest number that's represented on this number line, that's part of what's been highlighted, since everything is highlighted, the smallest value is -infinity, and then On the right side, the highest value that would be highlighted is positive infinity. So the interval, the lowest number in this set is negative infinity, and the highest number in this set is positive infinity. And this is what's known as interval notation. And this is the preferred notation in this textbook, and in this course rather, for representing domain is interval notation. So another function we look at here, 2x squared minus 3, this is a quadratic function. We got to think if a number was used as an input for x, the first thing that happens to it is it's squared, and then it's multiplied by 2, and then we subtract 3. So you got to think, is there a number that we can't square and then multiply by 2 and then subtract 3? Because remember, the domain is the set of all possible inputs. So sometimes rather than thinking of what does work, it's sometimes quicker to think about what doesn't work as an input. Is there a value for x that can't be squared and then multiplied by 2? And the answer is no. You can square any number, any real number, and you can multiply that number by 2 and then subtract 3. So the same thing, the domain for this function, and the domain for any quadratic for that matter, is all real numbers, or negative infinity to positive infinity. That would cover the whole real number line, meaning any number in the real number system could be used as an input. So that might be something that helps you remember. Any linear function or any quadratic function always has a domain of all real numbers. So we have a couple of examples of functions that have what are called restricted domains, or a domain where certain values of x aren't valid as input. For example, this one, f of x equals x plus 4. What we have here, this is called a rational function. Rational, from the word ratio, means essentially fraction. We have a numerator and a denominator, and you can't divide by 0. You can't have 0 in the denominator of a fraction. And so one problematic value of x cannot equal negative 4. If you plugged in a negative 4 for x and then added 4, you'd have 0 in the bottom of a fraction, and you can't divide by 0. So x does not equal negative 4. This is known as an excluded value in the domain. So the domain is all real numbers except for one single value, negative 4. So as a verbal statement, you would say the domain is all real numbers except for negative 4, or excluding negative 4. If you want to use, or if not that you would use this to answer on an exam, but the set notation would be the domain is all values of x such that x does not equal negative 4. But using interval notation, and again, for many students it's easier sometimes to visualize it on a number line first. If we took a number line, and I've got negative 4, everything on that number line is supposed to be highlighted except for negative 4. So what we can do is put an open circle on negative 4. That excludes negative 4. But then we can highlight everything else, both to negative infinity and positive infinity. And what we end up with is the number line has been broken up into two intervals. This interval is negative infinity to negative 4. And this interval over here on the right side is negative 4 to infinity. And the grouping symbols that you would use here are either parentheses or brackets. Parentheses means not including, and a bracket would be including. By bracket I mean this symbol. Brackets means including. Parentheses in this case is not including. And since we're not including negative 4, we have to use parentheses. So how you would represent this is the domain is negative infinity to negative 4, and then we use a symbol here, it looks like a U, it's called union, negative 4 to positive infinity. This would be what you would circle as an answer on an exam if you were trying to state the domain of that function 1 over x plus 4. Another common function that has excluded values is a family of functions called radical functions. In this case, it's a square root. And hopefully you remember that you cannot square root negative values. Matter of fact, before we get to x minus 3, let me go ahead and erase part of this here. If we just had f of x equals the square root of x, then the only values you could plug in are values that make this function defined, and the only time that the square root is defined is if x is greater than or equal to 0. So the domain would be all values of x such that x is greater than or equal to 0, or including 0 would be bracket from 0 to infinity. So you've got to remember that when you're taking a square root, you can only take the square root of positive values. So let's go back to the function we started with, the square root of x, I think it was x minus 3. In order to square root any expression, and it doesn't matter what is underneath the square root, in order to square root or take the square root of any expression, that expression must be greater than or equal to 0. So what you do in any case when you're trying to evaluate the domain of a square root function, you take that expression, in this case x minus 3, and it must be greater than or equal to 0 in order to be defined, otherwise you wouldn't be able to find the square root of it. And then you simply solve the inequality. So if you add 3 to both sides, x is greater than or equal to 3. So represented on a number line, we have 3, and greater than or equal to means I'm going to include 3, so it's a filled in circle including 3, and then greater than would be in this direction. So to represent what I've drawn here on a number line, the grouping symbol that means including is a bracket, and the lowest number in that set is 3, and the highest number in that set is infinity, or in that interval is infinity. So the domain is 3 to infinity, including 3. So one more to look at that kind of combines both of those ideas is we have a rational function with a square root in it. So there's a couple of things to consider when looking at the domain. First of all, we have a problem here in the denominator where you can't divide by 0, so x cannot equal 3 is part of our exclusion or domain restrictions. So far x can be anything except for 3. But then we also have to consider this. In order to evaluate the square root of x plus 1, it must be true that x plus 1 has to be greater than or equal to 0. And if we solve that inequality, we have x is greater than or equal to negative 1. So there's two parts to consider that are going to comprise our domain. X has to be greater than or equal to negative 1, but it also has to be true that x can equal 3. So if we were to think about this on a number line, starting at negative 1, and it's going to include negative 1, so I'm going to have an open circle, or sorry, a closed-in circle because it includes it, and it needs to be greater than, so that's to the right. But once we get to 3, it's not including 3, it can't equal 3, so I'm going to put an open circle at 3 and then continue on to positive infinity. So what we have as far as numbers in the set, or numbers being represented on this number line, there's two intervals. There's an interval that includes negative 1 to 3, not including 3, and also an interval from 3 to infinity. And this would be our domain. Okay, so that wraps up what we needed to discuss, or what needed to be presented at least, in section 2.1. So just quickly to wrap up, going back. Evaluating a function was our first learning target. So evaluating a function could be at a numerical value like 2, or it could be evaluating a function at expressions like that. We talked about a piecewise function. One of the more common mistakes to be aware of is students try to place one input into all 3 parts or all 2 parts, however many parts there are. That doesn't work. Remember, it's a function. One input gives you one output, so you've got to decide where that input goes based on those inequalities. And then we talked about a difference quotient, and a difference quotient really is just the slope of a secant line between 2 points, and it uses this formula right here. And we talked about finding the domain of a function. Sometimes for linear functions and quadratic functions, it's just a matter of the domain is all real numbers. When you have some of these more specialty functions like a rational function or a square root function here, then you have domain restrictions, and you have to figure out what those exclusions are.